Okay, so I just showed you this beautiful, beautiful theorem. The finite field method for computing the characteristic polynomial of a hyperplane arrangement. And let me remind you how that goes. So by now you're familiar with the definition of the characteristic polynomial of an arrangement. It comes from the Mobius function. And I think that by computing it in a concrete example, you've realized that this is not so much fun to do for a large arrangement. I mean, it's complicated to do it manually, to do the intersection posit, to find the Mobius function. That's pretty tricky stuff. But then there's this wonderful method that tells you that to compute this polynomial, you can do something very different, which is this only works under the assumption that the arrangements have integer equations, or at least rational equations, which you then make integer by multiplying by a constant, right? So you take your arrangement, you take a large prime Q, and then you reduce the arrangement over the finite field of Q elements. And then what you do is that you count the number of points in your vector space FQ to the D, which are on none of the hyperplanes of the arrangement, and that's going to give you by the way, you should realize that if you look at the right-hand side of this thing, then you have no reason to believe that that should be a polynomial in Q. You're just doing some counting problem. It depends on Q, and it's not at all clear that it should be a polynomial. But this theorem tells you that not only is it a polynomial, but it's the polynomial that we're looking for. It's the characteristic polynomial. Yeah. And the last time we did a couple examples of this, we did the example of the coordinate hyperplanes, which was pretty simple. And then we did the example of the braid arrangement, which is more interesting. And we saw that in both examples, it's very easy to use this method to get the characteristic polynomial. Okay. So what I want to do today is talk about another very interesting example. And so the topic of today is what's called graphical arrangements. Graphical arrangements, they come from a graph. So G is going to be some graph on the vertex set square bracket n, which remember is the numbers from 1 up to n. Okay. And given that graph, I'm going to define the graphical arrangement of G, which lives in Rn, is given by the equation. So we denote it by A sub G. And it has one hyperplane for each edge of the graph. And the hyperplane is just going to be given by xi equals xj. Okay? So you take each edge of the graph and make a hyperplane out of it. So just to make sure that we're clear, let's do an example. So maybe my graph looks like this. And this is vertex 1, 2, 3, and 4. So then there's an edge between 1 and 2, so I get a hyperplane x1 equals x2. Then 1, 3 gives me x1 equals x3. 1, 4 gives me x1 equals x4. 2, 3 gives me x2 equals x3. And 3, 4 gives me x3 equals x4. And so that's a hyperplane arrangement. It lives in 4 dimensions, and it consists of 5 hyperplanes. And by now you know that there are ways of visualizing this. You already drew an example harder than this one in your previous homework. By the way, the grade for that homework is in your inbox now. I just sent it. Anyway, so you know that in this case you would be able to draw this if you worked hard at it. But in general, this is going to live in very high dimension. You know, if the graph has 20 nodes, then this is going to live in 20 dimensions, and we're not going to be able to draw it. But that's fine. I mean, those are the equations of the hyperplanes, and that's what we get. So let's do another example. The complete graph. So what do you get with the complete graph? You basically say, okay, you know, I have n vertices, so that tells me I have n variables, and now every pair of vertices is connected. So for every I and j, I need to have the equation xi equals xj. And so that's exactly the braid arrangement, right? Every single equation of the form xi equals xj. The braid arrangement. Which has equations xi equals xj for all I and j between 1 and n. Okay? Okay, so this might seem like a strange idea to make an arrangement out of a graph, but you'll see why I do it. You'll see why I do it. Now, a natural question, given what we have done so far with arrangements, is what is the characteristic polynomial of this graphical arrangement? Okay. And right now we have two ways of doing that. One way is through the Mobius function. And if we were to do that, that would mean that we would have to take every possible intersection of all these hyperplanes, make a poset out of them, figure out what the Mobius function is. And this just turns out not to be so nice. Sometimes we're very lucky that the Mobius function goes 1, minus 1, 1, minus 1, etc. But when you do this here, you're going to find that there's just not anything so interesting that you can find there. Okay? This is just not so clear. Not clear what you get. Okay, from the Mobius function, it's hard to tell what's going on. Now let's see what the finite field method tells us. That's our second alternative. So what does the finite field method tell us? It says, okay, pretend that you don't live in Rn, pretend that you live in Fq to the n. Okay, so now the coordinates are not going to be real numbers. They're going to be numbers between 0 and q minus 1. And then we need to count the number of points in Fq to the n. In this case, we live in n dimensions on no hyperplane of the form xi equals xj, where I and j are connected in the graph. Okay? Okay, so well, think about it for a second. So this is the graph that we were looking at there, and now we're looking for points x1, x2, x3, x4, which live in Fq to the 4, such that x1 is different from x2, x1 is different from x3, x1 is different from x4, x2 is different from x3, and x3 is different from x4. Right? That's what I need to do. And it turns out actually that there's a useful way of thinking about this. I mean, from this point of view, finite fields actually are not, you should definitely not be intimidated by this. Here, each one of these numbers is just a number between 0 and q minus 1. And so all I'm saying is assign numbers to the vertices, right? So that's what you do here. And make sure that you don't assign the same number to two neighbors. You don't assign the same number to 1 and 2, to 2 and 3, to 1 and 3, and so on. And this is going to look a lot simpler if instead of thinking that 0, 1 up to q minus 1 are elements of some finite field, let's just think of them as colors. Okay? So really, what I'm asking you to do is, I give you a bunch of colors. I have q colors, right? And then I say, color the vertices. So maybe you color this guy purple. And that means that because you color this guy purple, you don't get to color this one, or this one purple, because they're neighbors. Okay? So maybe you color this one red. Okay? And then here, this guy, it can't be purple, it can't be red, and I only have 3 colors. So that means that I'm going to have to use orange. And then for this one, it can't be purple, it can't be orange, I only have 3 colors. So it's going to have to be red. And that's it. So it's really a counting problem about how you can color this graph. So let's say this in friendlier terms. Number of ways to color. Just because that's what I had in my hand at that time. In that case, q is 3. But q is the number of colors that you have. So number of ways to color the vertices of G with q colors so that no two neighbors get the same color. Okay? Let's call this a proposition, even though it's a very simple observation. It's just translating the result to this setting. But the thing is that if you've taken a graph theory class, maybe you've seen this before. There's a name for this. This is called the chromatic polynomial of a graph. And again, if you look at this right-hand side, it should not be immediately clear to you that what I'm defining here is a polynomial. I'm saying, giving q colors, what is the number of ways of doing a certain thing? And a priori, it's not clear that there should be a polynomial. But because it's equal to this, it must be a polynomial. Right? And not only that, it's the polynomial that we're looking for. Okay? So this is, I forgot the AG, right? So here, this is the characteristic polynomial of AG. And this is called the chromatic polynomial of the graph. Of the graph G. Okay. And in graph theory, they call this chi sub G of Q. So then chi A sub G and chi G are equal. So you see, as far as graphical arrangements are concerned, finite field method is definitely what you want to do. It's just a lot simpler, and it translates this into a nice, simple combinatorial question. Okay? So I don't know. Maybe we should just compute it for this graph just to see how this works. So the characteristic polynomial is the number of colors, the number of colorings, supposing that now, just like Nick said, I don't have 3 colors, I have q colors. So imagine that I have q colors right here, and let's count the number of colorings of this graph. Okay, okay, let's do it like this. I'm going to ask you to look up because I'm just going to write, when this is done, you're just going to see the answer on the board. And the explanation is what is my hand waving. Okay? So how many ways are there to choose this color? Q, you could choose any color, right? So there's Q possibilities. Okay? Now, how many ways are there to choose this color given that you already chose this one? It's Q minus 1 because you can choose any color except for the one that you put here, whatever it was. So Q minus 1. Okay. Now what about this color? How many choices are there? Q minus 2 because it's Q colors, but you can't use this color and you can't use this color. And these two are different colors. So Q minus 2. Okay. And then maybe I should go find another color. This one, how many choices are there? Q minus 2 because, again, you have Q colors, but you can't use this one, you can't use this one. Okay? And so the characteristic polynomial of this arrangement is Q times Q minus 1 times Q minus 2 squared. Okay, this is really nice, and it's kind of hard to believe that you're computing characteristic polynomials. I think so far you think of these as hard things, but in this case it's a nice, fun combinatorial problem that is not too bad to solve, at least in this special case. Okay. So is this clear? It's good. Okay. So maybe we should talk a little bit about what do we need to assume about G?
Simple or something. Like there's no multi-edges or loose edges or loops and things like this.
The only thing that I need to assume is that I don't have self loops. So edges from I to I. Because then it would be impossible to solve this coloring problem. But otherwise it's fine. Okay, so I don't know if you So let me tell you a very important theorem concerning this. Say that G is planar if it can be drawn in the plane without any edges intersecting. Okay, so that's an example of a planar graph because I was able to draw it without the edges crossing. So here's the theorem. If G is planar, then the characteristic polynomial evaluated at 4 is not 0. You guys know this theorem? This is the four-color theorem. The four-color theorem, which tells you that if you have some map, and maybe I actually picked a nice example here, so let me use the same one. So this is supposed to be some map of some territory. Maybe like this. Just a second. I need to do this right. Yeah. Okay, so this is called the four-color theorem. It was proved by Apple and Haken in '76, but actually it was conjectured in 1852 by Guthrie, this British South African mathematician. And he was just coloring the map of England, and he realized that he was able to color it with only 4 colors. Okay. So here's a map And I want to show you that it's not possible to color it with 3 colors. Now, of course, the point is that if you have 2 neighboring countries in the map, you don't want to give them the same color because then you won't be able to tell the border, right? So let's say that this is blue. Okay? And let's say that I'm going to try to only use 3 colors and see if I can do it. So let's say that this is red. That doesn't really matter. Okay? Then this one has, so blue, red, and orange is what I have. So this one has to be orange because it can't be blue or red. This one is red because it can't be blue or orange. This one can't be blue or red, so it's orange. This one can't be blue or orange, so it's red. This one can't be blue or red, so it's orange. This one can't be red or orange, so it's blue. But you get to this one, and it can't be blue, it can't be red, and it can't be orange. So I got stuck. So I cannot do this with 3 colors. I need a 4th color, like purple. Okay. So this map can be colored with 4 colors, and what Guthrie conjectured in 1852, and Apple and Hacken proved in, this is 1976, not 1976, is that no matter what country you have, it can be colored with 4 colors. Okay. So what's the connection? Well, let me erase the coloring. And what we're going to do is we're going to put a node for each country. Okay. And then I'm going to connect neighboring countries. Okay, so then I get this picture. And then you see that the problem of coloring the map is precisely the problem of coloring the graph in this way. This is, by the way, these are called proper colorings. Okay. And so this statement is precisely saying that the number of colorings of a graph, a planar graph, with 4 colors, it's not 0, it's at least 1. Okay, so that's kind of a gimmicky way of stating the four-color theorem. Okay. By the way, maybe I should tell you, in case you don't know, because it's a really interesting story, I think, that, well, as you can see, this problem was open for almost 125 years. And when this proof came out, it's kind of a crazy proof, because first of all, it's a paper that it's over 125 pages long. And the paper has some very intricate graph theory. And then at the end of the paper, what they do is that they show that if there were any counterexample to this, if there were any country that could not be colored like this, then it must contain one of the following 1936 countries as a subcountry. So they basically reduced the problem to checking it for 1936 different maps. Okay, and then these were pretty big maps, and they had a computer to do the check for them. And this was the mathematical world was up in arms about this, because it was the first time in history that a computer had been used in mathematics to give a proof. And this was a proof that nobody could check. They just had to trust that these guys had written the computer program correctly, and that the computer program didn't make any mistakes. And really, people didn't accept this as proof for a long time. But I think by now the community is not so conservative, and we're humble enough to realize that computers can do things that we cannot do. Yeah. So people are working really hard. That's a very good question. People are working really hard, and there are simpler proofs, but somehow the simple proof hasn't been found. And, well, it's debatable whether it exists or not. And I should tell you that a lot of this machinery that you see here was developed in the hope of giving the simple proof. Because there was a hope that, well, here we have some kind of larger machinery where we can state this result, and maybe we can prove it. Okay? So, for example, people thought, okay, well, what we're trying to do is really understand where are the roots of chromatic polynomials. And so they said, okay, let's investigate roots of chromatic polynomials. And it's very interesting because, for example, there are some nice results about this. For example, so this is the complex plane, and let's try to plot the roots of chromatic polynomials. Okay, so what Apple and Hacken show is that 4 is not a root of a planar graph. Okay? And what people have been able to show, so here's 1, 2, 3, 4. What people have been able to show is that there are no roots of the chromatic polynomial here, in the real line after 5. And the hope was, okay, well, if we were only able to push it a little bit longer, then we would actually have a conceptual proof of this result. But nobody has been able to do that. So that's interesting because the planar graphs can't have roots over here, but at the same time, people have also proved that if you plot the roots of all possible chromatic polynomials, that's dense in the complex plane. So even though 4 is not a root for a planar graph, actually, this is dense, so there's roots all around it, and this is a dense picture. Everywhere there's roots of chromatic polynomials. Okay. And I think this is kind of a fascinating story, and the hope was that it would give the proof, but it hasn't yet. Okay. Maybe you guys can do it, I don't know. But so far, there are a couple of better proofs, but nothing as simple as one might. Especially nothing as simple as what would have been expected at this time. I mean, graph theory at that time was a game. And now it's a huge theory, and we have a lot of tools, and still we haven't been able to give a very nice proof. Okay. So let's talk about another interesting consequence of this. So here's a theorem of Stanley. From 1973. It says the following. So Stanley was one of the pioneers of plugging in weird numbers into polynomials in a way that shouldn't make sense. So he said, what happens if we plug in -1 into this chromatic polynomial? Well, that shouldn't make any sense because we're talking about the problem of coloring a graph with q colors. And so somehow this would be like coloring a graph with -1 colors. That doesn't seem to make a lot of sense. And the point, of course, is that this is true for q, a positive integer. Right? Because this right-hand side only makes sense for q, a positive integer. But that's not going to stop him. He's going to plug in -1, and he found that this is the number of acyclic orientations of the graph. And an acyclic orientation is a way of orienting the edges of the graph without forming any cycles. And I should put an absolute value here. Okay. So to make sure that we're clear again, let's do this for the graph that we're considering here. So what you're supposed to do is put an arrow on each edge. Okay, so maybe we do it like this. Okay, so that's an orientation. Is it acyclic? It's not, because you see that there's a cycle here, a directed cycle. Okay, so this is not acyclic. Okay, and then you could fix it in many ways, right? So all you have to do, for example, is just change this to face the other way, and then you'll see that there's no cycles. Okay. Okay. So let's prove this. Well, it turns out that actually we have a really nice tool here, because we already saw one instance where we plug in -1 in a weird way. We do it precisely for characteristic polynomials. We saw that if you plug in -1 into a characteristic polynomial, you're going to get the number of regions of the arrangement. Okay. So then what you can say is, if you plug in -1 into the chromatic polynomial, well, because the chromatic and the characteristic polynomial are the same thing, that's just like plugging in -1 here, and we know that that's the number of regions of the arrangement. With absolute values. Okay, so here we're using Zaslavsky's theorem. And then what we could try to do is figure out why the number of regions of the arrangement equals the number of acyclic orientations of the graph. Okay. Now, how do we describe a region of AG? Well, if you want to describe a region of an arrangement, what you have to say is, for each hyperplane, are you on the positive side or are you on the negative side? Right? That's how we describe regions. So for each one of these equations, in other words, for each edge, decide, is xi less than xj, or is xi bigger than xj? Yeah. So are you on the positive or on the negative side of the hyperplane xi equals xj? You have to make that decision for every edge, right? But then you see that, I mean, it doesn't take so much imagination. If we're looking for a way of orienting the edges, we're saying for each edge I and j, either say this is less than this, or say this is bigger than this. So what we should do is just, if it's less than this, then let's say that by putting a less than sign here. And if it's bigger, then let's do this. Let's say it's bigger. Okay. So to specify a region, I have to do this. I have to put an orientation of the graph. Okay. Now, so given a region, there must be an orientation that labels it. But the question is, when I orient it, do I really get a region or not? And let me give you an example. Now, I wrote it here. So let's say that I take each one of these hyperplanes and I choose a side. So I choose, for example, that x1 is bigger than x2, x1 is bigger than x3, x1 bigger than x4, x2 less than x3, and x3 bigger than x4. Okay. So I'm telling you, I'm the region that is on the positive side of this hyperplane, on the positive side of this hyperplane, positive side of this one, negative of this one, positive of this one. Now, could I possibly be that region? If you look at the inequalities, am I really describing a region here? No, why?
The second equation in the first column, the first equation in the second column.
x1 is bigger than x3. x3 is bigger than x2. And where's the contradiction? It's a little bit hard to tell, and actually it's a little bit easier if I just give you this picture. And I did this carefully so that everything matched up. So you see the inequalities that I wrote there are precisely the way that I oriented this guy. x1 is bigger than x2. x1 is bigger than x3. x1 is, well, at least that's what I meant to do. Sorry, I meant to say x1 less than x4. Okay. x1 is less than x4. x2 is less than x3. And x3 is bigger than x4. Okay. So this system of inequalities I am encoding in this picture, and I'm asking you, is that really a region? And the point is that it's not, and the answer is precisely the cycle, right? Because I have a cycle here. This cycle is telling me, in your region, supposedly, x1 is less than x4, x4 is less than x3, x3 is less than x1. And you see those inequalities here. x1 is less than x4, x4 is less than x3, and x3 is less than x1. And that can't be. Okay. So that's not a region. And the reason it's not is that it has a cycle. Okay. So this orientation doesn't give me a region. Okay. Now, if we go back to the one that I wrote originally, where x1 is bigger than x4, and I ask you, is that a region? Then you'll see that what I'm doing, so if instead I change this to be a greater than, then that means that instead of this oriented like this, it's going to be oriented like this. And now there are no cycles here, which means that I can find numbers 1, 2, x1, x2, x3, and 4 such that they satisfy these inequalities because there's no contradiction between them. So that means that this new labeling, this new orientation, does give me a region. Okay? And so what we're saying is that the regions are precisely given by the orientations that have no cycles. And that's precisely what we were looking for. So the number of regions, this gives a bijection between the regions and the acyclic orientations. So the regions of A sub G and the acyclic orientations of G. Okay? And that finishes my proof. Okay. You guys have any questions about that proof? I really like this proof. I really like this proof, and for several reasons. But one reason is that actually, I mean, I could have stated this theorem without talking about geometry, arrangements, hyperplanes, anything. This is a combinatorics theorem about coloring a graph and about orienting a graph. Okay? But somehow this theorem fits beautifully into this framework, and basically, if you just plug in the theory of hyperplane arrangements into this graphical arrangement, then this is just what comes out. It's a direct consequence, which I think is pretty fun. Okay, so let's see how we're doing.
You can't say that the sine graphs are going to keep the correct characteristic on the chromatic component of the sine graph.
So I'm not planning on talking about sign graphs, but I think you should look at what happens with sign graphs. And I mean, I guess you have, yeah. So exactly, your homework assignment was basically doing almost this, but where you also allow xi plus xj, and that's like having edges with signs. And this theory works very nicely in that setting, and I wasn't planning on saying too much about it, but I'm happy to talk to you about it. So, but it does work out in that setting as well. Okay, actually, I am going to stop here because I need to get you guys to fill out these forms for me. So you probably know the drill because you've done it yourself. But so I just need you to fill out this form. I was just realizing, looking at it, that our budget crisis means that they don't provide pencils. So, so if I could ask you to, whatever pencils you have, if you could share them, make sure that the bubbles go in pencils, everything else can go in pen. And I'm going to tell you what you tell your students, that numbers are nice, but really what's more interesting to me is what's working well, what you would suggest could be improved, etc. So please take the time to give the most useful answers that you could possibly give. And I need a volunteer to deliver this upstairs. Somebody? Okay, Michael is going to do it. And behave because you're on film. But don't worry. They're not filming what you're actually writing on there. But anyway. Yeah. So thank you. The course number is Math 890.01. And make sure you spell my name correctly. There's only one L.